Let's now examine efficiency calculations for multi-stage systems. Consider a photovoltaic system modeled as an array of modules which converts the radiant energy of the sun into usable DC electrical output. Wires that transport the DC electrical output of the array to an inverter, which then converts the DC power output of the array into grid-compliant AC power for export. Let's examine each stage of this three-stage system separately. Let's say the array is made of 8 15% efficient modules. Each module is 1 meter by 1.5 meters for an effective surface area of 1.5 meters squared each. If the sun shined at STC conditions, or 1000 watts per meter squared, see if you can determine the usable electrical power output for this 8-module array. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's first determine the total surface area of the array. 8 modules, each with a surface area of 1.5 meters squared, represents a total surface area of 12 meters squared. Let's now determine the power input to this system. 12 meters squared times 1000 watts per meter squared demonstrates the array consumes 12,000 watts, or 12 kilowatts. Output is input times efficiency. 12 kilowatts times 0.15 demonstrates the array produces 1.8 kilowatts of usable electrical power output. Let's move on to the second stage of the system. Let's say the wires leading from the array to the inverter dissipate 50 watts of heat losses into the atmosphere. See if you can determine the efficiency and the output of the wiring. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. First, let's determine the usable power output of the wiring, where output is input minus losses. 1.8 kilowatts minus 50 watts yields a usable power output of 1,750 watts, or 1.75 kilowatts. Efficiency is output over input. 1,750 over 1,800 yields an efficiency of roughly 97.2%. Let's now move on to the final stage of our system. The inverter is known to be 98% efficient. See if you can determine the usable power output of the inverter. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Output is input times efficiency. 1.75 kilowatts times 0.98 demonstrates the inverter yields 1,715 watts, or 1.715 kilowatts of usable power output. Now that we've inspected each stage, let's examine the efficiency of the complete system. Ultimately, the system consumed 12 kilowatts of input to yield 1.715 kilowatts of usable power output. This represents a total efficiency rating of 1.715 over 12, or roughly 14.3%. Note how the efficiency of the complete system is less than the least efficient stage, in this case the PV modules themselves. You'll note that although the module stage is admittedly inefficient, the stages that follow this initial conversion from solar to electrical power are designed to be as efficient as possible to ensure any power extracted from this free and for all intents and purposes inexhaustible resource is put to good use. Additionally, note that it is possible to directly calculate the efficiency of the complete system by multiplying the efficiency rating of each stage. 15% times roughly 97.2% times 98% yields a complete efficiency rating of roughly 14.3%, as we'd expect. Let's end this lecture with another illustrated example of multi-stage system efficiency. Consider an industrial wind turbine modeled in the following fashion. A rotor consisting of the blades and hub intercept a column of moving wind and convert the mechanical power of the moving wind to the rotational movement of a shaft. Let's say the rotor stage is 30% efficient. The main shaft drives a gearbox, which converts the low-speed, high-torque movement of the main shaft into high-speed, low-torque movements of an output shaft suitable for electrical power generation. The gearbox stage is known to be 94% efficient. I should note that the terms high-speed, low-torque are only relative in nature. The high-speed shaft of a modern horizontal axis wind turbine has more than enough torque to rip your balls right out of your sockets should any portion of your anatomy ever get entangled with it. Make sure there's a protective shroud between you and it anytime it's rolling. The output shaft drives a coupling. The coupling compensates for misalignment between the gearbox and the generator and allows the pair to be taken apart for maintenance and service purposes. The coupling stage is known to be 95% efficient. The coupling drives a generator. The generator converts the mechanical power output of the coupling into electrical power. The generator stage is known to be 93% efficient. The output of the generator is fed to a converter that cleans up the power to ensure it's grid compliant and suitable for export. The converter stage is known to be 98% efficient. Finally, the output of the converter is fed to a transformer that steps up the voltage to ensure it's suitable for transmission. The transformer stage is known to be 92% efficient. Let's say this wind turbine has a rotor that spans an increased diameter of 120 meters and is experiencing wind speeds of 12 meters per second. See if you can determine the total efficiency and the power output of this complete wind turbine. To do so, you'll probably need the following information. The area of a circle can again be calculated as pi over 4 times the diameter squared. The mechanical power inside a moving column of fluid can be calculated as half the density of the fluid times the area of the column times the velocity of the fluid cubed. Finally, let's assume the density of the air is 1.225 kilograms per meter cubed. If you feel you're up to the challenge, by all means, pause the lecture and try this by yourself. If you're tracking, you should have obtained the following values. First, we need to determine the rotor swept area of a turbine with a diameter of 120 meters. Substituting a diameter of 120 meters into the circular area formula demonstrates this turbine has a rotor swept area of roughly 11,309.7 meters squared. Now we determine the input mechanical power. Substituting the density of 1.225 kilograms per meter cubed, the area of 11,309.7 meters squared, and the velocity of 12 meters per second into the mechanical power formula demonstrates this turbine is effectively consuming 11,970,222 watts, or roughly 12 megawatts of wind power. We could calculate each stage's contribution individually, however, you'd be stupid to do so because it's much faster to directly calculate the total efficiency of the larger system by multiplying the efficiency of each individual stage. 30% times 94% times 95% times 93% times 98% times 92% yields a total efficiency of roughly 22.5%. Output is input times efficiency. Roughly 12 megawatts times roughly 22.5% yields a usable power output of roughly 2.7 megawatts. Again, you'll note the efficiency of the complete wind turbine is less than the least efficient stage, in this case the rotor. Although the rotor stage is admittedly inefficient, the stages that follow this initial conversion are designed to be as efficient as possible to ensure any power extracted from this free and for all intents and purposes inexhaustible resource is put to good use. Alright, that's about it for today. In conclusion, this lecture examined efficiency calculations for single-stage and multi-stage systems by way of a series of illustrated example problems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.